Hi, welcome to my YouTube channel, ICCAP Tutorial 7. We'll focus on MDM data format today. MDM is a common data format for ICCAP. It's an ASCII-based file with its own structure. We have 4 example data here. We'll use the example data files to show the structure directly. The first one is a hemmed data for IDVG curve. So we can take a look at this one. So you can see the data structure starts with a header file from the begin header and header. This is the header file part. And this part defines the input-output information in like the input VD, VG, and output is ID, IG, and T. And followed by the input-output name, there's still a lot of information. So we need to make clear what are those informations. So for the input, we take VG as an example. The V is the mode, and the G ground SMU 0.1. Those are the detailed information for this one mode. Let's take a look at the template first. For the mode, ICCAP supports input-output with a lot of different mode types. And the VG input, it is a V mode. So for the details followed by the V mode, you have the nodes, the SMU used for measurement for this one node, and the compliance. Now let's go back to look at this example again. V is the mode name and its voltage, and the connection node is G to ground, gate to ground, and the connection is SMUB and compliance 0.1. From here to the end, this is another item. We call it a sweep type. For the sweep type, we also have a lot of options inside ICCAP. So the current one we're using is LIN, as means linear, as a linear sweep, and followed by the linear. There's a sweep order, start, stop, number of points, and step size. So we understand this, is easier to understand the example file. Let's go back. So for the VG, it's a linear sweep. It's the first order sweep. Start from -3 to 1.8 volt, 97 points. The steps 0.05. And for the sweep order, for new users, it may be a little bit confusing sometimes. So it's still easy to understand. For this sweep, we have 2 inputs, VG and VD. For this measurement, we are measuring multiple IDVG curves for different VDS value. In this case, VG is the first order sweep. VD is the second order sweep. We call this sweep order 1, sweep order 2. This is how it is defined. Then let's take a look at the output part. Output definitions similar to the input definition. You have the mode. Here it is I is current. For ID and IG is current. For T is voltage. The DG to ground, those are the node connection. SMU is the unit used for measurement. And then the B here means the output include both simulation value and measurement value. Because this data can be used for simulation as well inside ICCAP. So if you put M here, it means measurement only. If you put S here, it means a simulation only. But if you put B here, it means both measurement and simulation. Now let's take a look at the data part. The data part can be separated to different data blocks. Begin dB to end dB, this is one data block. And inside this one data block, there's a ICCAP variable. So the input is VG, output is ID, IG, T. We are sweep VG and measuring ID, IG, and T. And in this sweep, VD has a constant value, 0.05. VG and VD are the 2 inputs, but we can sweep only one at each time. The other one is a fixed value, like VD is fixed here. So the VD sweep, we actually separated it to several different data blocks. Each ICCAP variable stands for one VD value. So this is how it is defined. So how many data blocks do you have? It depends on how many VD value you have here. If we look at ID output only, so each data block is one IDVG curve with one VD value. And then when you plot all the IDVG curves together on one plot, you will have multiple IDVG plots, and each of the curve has one VD value. So it is IDVG curve with different VD value. Okay, this is the first example. Now let's take a look at the second example. It is a BGT forward download data. You can see it still had a header, defines the input, output, and then the data block. For this one data, there's something special here because we're sweeping VB and VC together with synced value. And since the sweep type we support sync, you can give it sync here. And let's check how the sync sweep type works in the template. If you use the sync sweep type, followed by the sync, there is a ratio. So the ratio to the original one you're syncing with, and the offset and the master sweep. Now let's go back to the BGT example. The sync with a ratio, it is 1. And so exactly, VC will be exactly follow VB. No offset, and it's following VB. This is how the sync works. And then in the data block part, you will see VB and VC. They're both as inputs with synced value. And then mirror IB and IC. This is the second BGT example. Now let's take a look at the third one. The third one, similar to the second one, but you see has another one output is better. This one is not a directly mirrored data. It's actually calculated from the gamma curve. So, but you can still save this data to the MDM file after the calculation. It will no longer has the node connection those problem because it's calculated not directly mirrored. It's not necessary anymore. And then after the calculation, you can save the better data here in the data block. Now the fourth example is a 2-port S parameter data. So the input, output, the header part, then data block part, no big difference with what we've seen before. It's just the mode here is frequency, and it's also a linear sweep. Then the database part, you see the first order sweep is actually frequency, and then the output, what you have is as parameter S11, S12, S21, and S22. And each of them has its real and imaginary part. Okay, with the 4 examples, I believe now you understand more about the MDM data. Thank you.